Hi everyone. We have reached part 3 to our unit analysis notes. In this video, we're going to look at some of the more advanced problems. Okay. It actually turns out that some of them are fairly easy computationally, but these are really long paragraphs to get through, so let's dive right in. Okay, so the first two actually don't have those long paragraphs I was talking about. These first two are just very weird looking. However, if you can do these ones, it demonstrates that you can pretty much do any sort of dimensional analysis problem when you're thrown new or unique dimensions. Okay, so yeah, this first one, we're given a whole bunch of things here. We're going to treat these at the top, these conversions, as if they're on that measurement equivalency sheet just for this problem. Okay, and do remember that that word per here, right, that could mean our fraction or an equals, either one. Given that the other ones are all equals, I'm going to write them that way for now. So the actual question says to convert 18 jigs to zigzags per bag. So we're converting the 18 jigs. We want to end up with zigzags per bag. And remember that per, in this case, would be the fraction bar. We want to end up so that we have zigs and zags in the top and bag in the bottom. All right, this all sounds really crazy, so I'll try to be very clear and enunciate well. Start with what we're given as always. We have 18 jigs, not per anything, so I'm going to put it over 1. And then we need to set up our conversions. These are definitely not on the sheet that we had, so we're going to look at the ones that we were given. We're just going to go through and see where we see jigs, which is right here. Okay. So that means we need to use this conversion. Right now, jigs is in the top, so we're going to put the jigs on the bottom. And using our conversion, we can see that 9 jigs, so I'm putting the 9 in the bottom there, is equal to 2 jags. So we put 2 jags in the top. Something that I think is really helpful on these weirdo looking problems, once you've used one of these equivalencies, you don't want to use it again. Otherwise, you're going to end up working backwards. So if you want to just mark this one off somehow so that you know you used it, do that. All right, so our jigs cancel out, one on the top, one on the bottom. Now we're in jags, not one of the things that we want, so we need to keep going. If we look through those conversions at the top, we see jags in 2 of them, but the first one here we've already used, so we don't want that. We definitely want the one on the end there, 6 jags per or equal to zig. Jags is currently in the top, so let's put jags in the bottom, which would be 6 jags by our equivalency here. And then in the top, that's equal to zig. And if it's not given, remember it's a 1. So 6 jags is equal to 1 zig. We've used this equivalency, so I'm going to mark it off. I don't want to accidentally use it twice. Jags cancel out, and now I have zig, which is good. I wanted a zig, right? That was one of these ones I wanted. So I don't want to get rid of it. What that means is I'm not going to put zig down here like we have in the past. Right? I don't want a zig right there. And this is where sometimes students get a little stuck. They're like, well, if I don't put a zig there, how do I keep going with this? Well, you have a couple of options. And you're just going to look at what you want to end up with, and you're going to put one of those things in there. Okay? So let's say we're looking for the zags. If we look at the equivalencies that we have left, only one of them has zags in it, right here. So we're going to put that in there. We're just going to force it in there, essentially. We know we want it in the top, so we're going to put the 7 zags on the top. Now you can see in the top we have zig zags like we want. Okay. From our equivalency though, that 7 zags is equal to 4 bigs. So I have to put the 4 bigs on the bottom here. That way, remember these two things are equal. That means they're really a 1 via division. So we're okay. I'm going to mark that equivalency off. So only one equivalency left that we haven't used, so I'm guessing that's what's coming up next. We do need to keep going because the bottom is bigs. That's not what we want bag. So hopefully this one will help us. Last equivalency says 3 bigs per or equal to bag. That's usable. Bigs is in the bottom, so I'm going to put the bigs in the top. 3 bigs goes in the top there, equal to bag, or 1 bag, right, in the bottom. Bigs cancel out, and bag is in the bottom now, which is what we wanted, so that's good. So if we look at our units that are left, we have the zig, zags, and then per, because that's our fraction bar, bag, which is exactly what we want. So this is how we can tell that we are officially done. All right, at this point, just like in every other one, just do the multiplication and division out to get your final answer. This one, I believe, works out to be 3.5, 3.5 zigzags per bag. I almost ran out of room there. Should have written it down below, huh? There you go on that one. All right, question 22 is very similar. This one always makes me think of green eggs and ham. I don't know if it's because of the hams and the sams and the scams, but it's crazy. I would suggest if you felt okay with the last one, following me, maybe try this one on your own. It is a slightly bit trickier, but it's definitely doable. Okay. All right, I'm going to go through it though, obviously. Again, we have all these equivalencies that we were given up at the top. We're going to basically use those in this process. We want to convert 3 yams, and we want to go to Sam scams per spam ham. Our pers are fraction bar, remember, so I want Sam and scam in the top, spam and ham in the bottom when we're done. All right, let's go for it. Start with what we have, 3 yams. Not per anything, so just a 1. Now let's look through the conversions we're given, and we're trying to find this yam, right? We'd like to get rid of some yam. Yam only shows up one place, and it actually is with yam lambs. That's okay. Okay. We just have to remember that we can't necessarily get rid of both of those. We can only get rid of the yam part. Okay. But we're going to use this. This says 5 yam lambs is equal to 6 scams. So we're going to put the 5 yam lambs in the bottom and the 6 scams in the top. That allows me to cancel out the yams, but remember the lambs are still there in the bottom. And just like in the previous problem, I want to mark off this conversion so I don't accidentally come back to it. All right, I got scams in the top. I actually want that, right? So that's good. I don't want to get rid of that. However, I have lambs in the bottom. Lamb is not one of these things I want in the bottom. I want spam or ham. So I need to find a way to get rid of that. So if we look through, again, the conversions we were given, in what's left, the second one in the middle column here is the only one that has the lambs. So we're going to use that. Right now, lambs is in the bottom. So in order for that to cancel, we need to put lambs in the top. And then our conversion says that 15 lambs, so we'll put that in the top, is equal to 2 whams, which is what we'll put in the bottom. Allowing us to cancel off lambs, 1 in the bottom, 1 in the top. And we're going to mark off that conversion as well. All right, so now we're at scams per wham. Don't want the wham, still not something I want in the denominator. I want spam or ham still. So let's just keep going. Again, looking at those conversions, we only see whams in one place that we haven't used, which is this second one in the first column. Whams is currently in the bottom, so we're going to put whams in the top. Our conversion says 8 whams in the top is equal to 9 hams in the bottom. Cancel the whams, top and bottom, mark off our conversion we used. Now we have hams in the bottom. That's actually something we want, right? We wanted ham, so that's good. We're gonna leave that. I'm not gonna try and convert it any further. But we're not quite done, right? We're like, yeah, we got 2 good things in the top, but we're still missing things. We're still missing Sam in the top. We're still missing spam in the bottom. Okay. You could do either one. I'm just gonna jump in with the top, I guess. I see Sam here, right? The second one in the third column, 2 jams equals 9 Sams. That's the only one I see with Sams in it. So I'm gonna use that. I want it to be in the top. So I'm gonna put the 9 Sams in the top, and then that's equal to 2 jams in the bottom. Mark that one off. And we have our Sams in the top now that we wanted. However, we now stuck jams in the bottom, and we don't want jams. We need spam. This is a ridiculous problem, right? All right, we're almost there. So a little bit further, we need to get rid of those jams. So I'm going to put jams in the top since it's in the bottom right now. We actually see jams in both of the 2 conversions that's left. The first one says 2 jams equals 15 rams. The second one says 5 jams equals 6 spams. We're going to use the second one, and that's because this has spams in it, which is what we actually want. Okay, we don't need the rams, we don't want them, so we're not going to use that conversion. This one is actually one that we didn't need at all. All right, so the conversion we are using says 5 jams in the top is equal to 6 spams in the bottom. Cancel our jams. And now we have spams in the bottom like we need. Looks a little ridiculous, but it's okay. Again, if we look at the units that are still left in the top, we have the scams and the sams, which is good. That's scam sams or sam scams, right? Multiplication order doesn't matter. And then per, because of our fraction bar, in the bottom, we have hams and spams, right? Ham spams or spam hams. Again, multiplication doesn't matter. So we have what we need in the top, we have what we need in the bottom. We're good. We just need to multiply through and divide. When all is said and done, this should be 90 Sam scams per spam hams. There you go. Again, I realize that this is an entirely fabricated problem and that it just seems utterly ridiculous some of the time. But the point is that you can follow the units and that you can do unit conversion even in an uncomfortable scenario where you don't recognize those units. Okay? Which is what might happen in another course when you're learning something new. You might be exposed to new units that you're not used to. All right, let's look at some of the more word problem-ish ones. So question 23 says, coming to grips with large numbers is often difficult to do. When I was in school, not actually me, this is one of my colleagues that made this. Okay. Anyway, they were assigned a year-long project to try and collect 1 million of something. And him and his partner collected bottle caps, and they got nearly 2,000. Not even close to 1 million, right? Okay. So anymore, though, we're talking about numbers in the trillions in the news all the time. So the intent here is to kind of put some of this into perspective. So it says, for example, the first stimulus bill during our COVID-19 pandemic, I did update this part of the question, known as our CARES Act, was $2.2 trillion. And our current national debt is over $26.5 trillion. So first thing, we're just going to kind of set aside those numbers for just a second, just so that you can see how large a trillion really is. I mean, we can see it written out as a number, but I think it's really hard for us to grasp those higher orders of magnitude. Actually, my husband teaches psychology. There really is. It's genuinely difficult for us to grasp that for a real reason. But let's just look at it. So the first part here, it says to help put these numbers in perspective, I thought it would be nice to know how long it would take you to spend $1 trillion. So we want to know how long it would take you to spend $1 trillion if you were required to spend 1 million per day. So I'm just going to call this part A. These aren't A and B, but I'm going to call it part A. So we're going to take that $1 trillion. We're going to use this rate here essentially per, right? That's an equals or a fraction bar, whichever one makes the most sense, as an equivalency in order to turn this into time. So we have $1 trillion. We got what? 1 trillion, no billions, no millions, no thousands, no hundreds, thousands, millions, billions, trillions. Good. Those are zeros, not sixes in any of those spots. Now you could do this with like treating millions or billions as units, but I think it's actually a little bit harder because then you would have to know the conversion, how many millions are in a trillion. It's easier to just write it out, honestly. Okay. So our units here in this case then are going to be the dollars. So we need to put dollars down here to cancel, and we're going to use that conversion. The spending rate is 1 million per day. So we're going to put the $1 million down here. So 1 million, no thousands, no hundreds. And that's per day. So that means $1 million on the bottom and 1 day on the top. Our dollars cancel out top and bottom. And then this would give us how many days it would take. I'm going to tell you right now, it works out to be really large. So I'm going to take this one step further and say, assuming it's not, you know, a leap year or anything, let's change this into years. So we're going to put the day on the bottom so it cancels. Okay. And there are 365 days in 1 year. So 365 days on the bottom is equal to 1 year in the top. All right, so now you can multiply and divide. I'm going to show you a little trick though to kind of make it easier if you have a calculator that can't handle typing 1 trillion into it. Because you're doing division here and these end in zeros, you can cancel them off. All right, so you have 1, 2, 3, 4, 5, 6 zeros in a million there in the bottom. So you can likewise cancel off 1, 2, 3, 4, 5, 6 zeros in that trillion. That way you don't have to enter as large a number into your calculator. All right, so now if you enter this and essentially divide by the 365, because we've turned this into just a 1, if you do this out, you should get 2,739.7 years. So what this is saying is if you had $1 trillion and you were asked to spend $1 million every day, it would still take you 2,700 and almost 40 years to spend all that money. And this is why some people are just so incredibly rich. Yeah, it's just unfathomably rich, right? Whatever, moving on. Let's look at the second part here. So the second part here says, I also think it is useful to consider how much of the current national debt each citizen of the US is responsible for, given that the current population is roughly 328 million people. So up above, we were told that the national debt is over 26.5 trillion. It's right around there. It's just a little bit higher and obviously fluctuates. So we're going to have that. We have the debt is 26.5 trillion. So 26 trillion, and then 500 billion. No millions, no thousands, no hundreds, right? Hundreds, thousands, millions, billions, trillions. That's how you could write 26.5 trillion, if you will. Notice how I put the point and then I said, nope, putting the comma and making the rest of my number. Okay. That's the current national debt, at least as of a few weeks ago. It's an insane amount of money. Right? And then we want to know how much each citizen is responsible for. So we're really looking at dollars per person, right? We have dollars on the top. We can make it per person. So we need to know how many people there are, which is our current population of 328 million there. So let's do that. 328, those will be our millions. There are no thousands, no hundreds. So then we can just do that division out. This is why I said some of them actually aren't super difficult in terms of computation, but knowing what to do can be a little bit tricky. All right, so same trick as before though. If you want to help with your calculator, you do have those 6 zeros at the end of each of these numbers at least. So we can get rid of 6, top and bottom, to make typing this in nicer. And then we can do the division out. And if you do that, you should get, looks like 69,371 dollars and 73 cents if you felt like going that far per person. Or we should say per citizen if that's what they're using. Okay. So almost $70,000 per person. It's more than my house is worth. All right. Again, I just really like that problem to help us understand how large some of these numbers truly are. So every single person in the US basically is responsible for almost $70,000 worth of debt. It's immense. All right, moving on to some of these other problems. So question 24 here says in 2014, the 128-story tall Shanghai Tower was the tallest building in China. I don't know if it still is or not. And the second tallest in the world, containing the world's fastest elevators. Again, I don't know if that's still true. Maybe there are faster ones now someplace else. These elevators run at a speed of 1,080 meters per minute. Right? That sounds important, right? So maybe we'll mark that for now. Assuming that each story in the building is about 16 feet, that also sounds important to me. So I'm going to underline that. Notice we're doing some math critical reading here, if you will. Determine A, how many seconds it will take a passenger to move from the first floor to the 128th floor, and B, how fast the elevator will travel in miles per hour. So let's just look at part A to begin with. Okay. So we want to know how many seconds. That's what we're going to end with. It'll take a passenger to move from the first floor to the 128th floor. So we're basically taking this distance of floors and converting it into time in seconds. Something I want you to be very careful of. When you move from the first floor to the second floor, you've moved through one story. Okay. Second to third, now you've gone through one more, so 2 stories. Right? So that means by the time you get to the 128th floor, you've only gone through 127 stories. Okay? You would have to go to the roof to go through all 128 stories. Okay? So just be careful of that. We're really saying this is to move through 127 floors or stories. So we're asked to take this and convert it into seconds. All right, so let's start with what we have, right? 127 floors, or maybe stories, if that makes more sense, whichever one you want. Not per anything, right? This isn't like a speed or anything, it's strictly a distance. So over 1. I need to get this into time. So that means I need to get rid of these floors or stories somehow. If we go back through the information that was given to us, we can see this part that we underlined here. It said each story in a building is about 16 feet. Okay. So what we're saying is that one story in the building equals 16 feet. That looks like an equivalence to me, so let's use it. Okay. So we have floors or stories in the top right now, so I'm going to put that one story in the bottom so I can cancel my stories. And one story we said is equal to 16 feet, so that'll go in the top. So now we're in feet. That's better. We're closer, but it's still not time, right? I need to get my feet and turn it into time. So this would depend on how fast that elevator is moving, right? The other part that we underlined back here, the elevators run at a speed of 1,080 meters per minute. So 1,080 meters is equal to 1 minute for an elevator in this building. Unfortunately, neither meters nor minutes are what we have, right? We have feet. We need to get rid of that. So this is where we need to go back to our regular conversion sheet. Okay? And we need to try to get to, meters would be the closest thing to feet, right? Those are both measurements of length. So we need to convert between them. So if you remember from our sheet down in the, what do I want to say? The US to metric conversion section under length, we had this little area. And the middle one here says the 3.28 feet equals 1 meter. We're going to use that. So we're going to stick the 3.28 feet in the bottom so that those feet cancel. And we just said that's equal to 1 meter, which we'll put in the top. So feet cancel out, and now we're in meters, which is good. That was our goal, right? Because now we can use the conversion that we just wrote down about the speed of our elevator. Meters is in the top, so we want to put meters in the bottom. Speed for our elevator is telling us that we want the 1,080 meters in the bottom, equivalent to the 1 minute in the top. So we're much closer. We're in time now at least, right? We're in minutes, but we want to know how many seconds. So we just got to take that one step further. I think everybody's okay with it, but if not, you do have that time section on your conversion sheet there. Minutes is in the top, so we're going to put minutes in the bottom. You know that 1 minute is equivalent to 60 seconds. And sometimes I use this SEC for seconds. Sometimes I just use S. They're both equivalent. It's okay. I've seen both abbreviations before. All right, we're in seconds. Hooray, we made it. Now we just have to multiply and divide out. When you do that, where do I want to put this? How about we put it right here? You should get 34.4 seconds. So just over half a minute. That is really quick, right? I think my stomach would be dropping to my feet on that elevator. That'd be fun though, be cool. Only takes 34.4 seconds to get from first floor all the way to the top of the 128th floor. Hope they got some smooth braking system. All right, let's look at part B. How fast, we want to find how fast the elevator will travel in miles per hour. Okay, so if we're talking about how fast it travels, that's a speed, right? So something like miles per hour, feet per second, whatever. We want to end in this miles per hour. Per, remember, is that fraction or equals? In this case, because it's what we're ending for, we're going to treat it like a fraction. We're saying we want miles in the top, hours in the bottom. So the speed that we were given is this right here. It can go 1,080 meters in 1 minute. We're going to use that. And I'm going to say because meters is a measurement of length, we're going to put that in the top because that miles measurement of length is what we want in the top. And minutes is a measurement of time, which is like hours, measurement of time. So we want that in the bottom. So what we're given this time is hidden a little bit, but it's the 1,080 meters over or per 1 minute. That's our speed as it was originally given. All right, we need to turn our meters into miles. Okay. We have a couple of options. We could go from meters to feet and then feet to miles. That's what we typically do. I should have mentioned in some of my other videos, if you like to go from meters to kilometers and then kilometers to miles, that's okay too, right? You might have things that are rounded slightly differently. I'm okay with that. So long as you're showing your work, that's what really matters. All right, our meters are in the top, so we're going to put meters in the bottom. That same conversion that we've used a few times now, 3.28 feet is equal to 1 meter. Our meters in the bottom, so make sure we put 1 meter, and that's equal to, like we said, 3.28 feet in the top. Meters cancel. And then we still need to get to miles. Feet isn't good enough, so that's why I added this US length a little bit from our chart here. Feet currently in the top, so I'm going to put it in the bottom. We've seen it in a few of our other ones. We know that 1 mile is equal to the 5,280 feet. So we'll put the 5,280 feet in the bottom, 1 mile in the top. Feet cancel. We have our miles, that's good. We're in miles per minute. We want miles per hour. Minutes in the bottom, so we need to put minutes in the top. In terms of time, we know that there are 60 minutes in 1 hour. So we'll put 60 minutes in the top, 1 hour in the bottom, so that our minutes cancel and we have the hours that we want. Go ahead and multiply and divide out. And we will get 40.3 miles per hour. And that is not slow at all, right? 40 miles an hour, that's faster than we typically drive in town. So buckle up, I guess, right? Pretty cool. Let's see what's next. Okay, yes, this problem I actually broke into 2 on my PowerPoint, the part A and part B, just because there's so many words and it doesn't really fit on the screen very well. This is another one that my colleague came up with, but I thought it was great because I've seen these Facebook posts floating around myself, right? Talking about the rate for a babysitter and what a teacher should be paid and all that. So yeah, he actually looked up the going rates in Chautauqua County. So let's look through it. All right, it says most of the numbers are found online, but they seem reasonably valid. I agree. The going rate for a babysitter in Chautauqua County is roughly $5 per hour per child. Additionally, you may need to provide transportation, sometimes meals for your babysitter. The average school teacher's salary in Chautauqua County is $53,000 before taxes, and they're contracted to work 180 days per year. Generally, teachers work 7:45 a.m. to 3 p.m. with a 45-minute break for lunch. And breaks in quotes because we know a lot of teachers work right through their breaks, right? The average class size varies from school to school and grade to grade, but let's use 20 as a generous estimate. And it probably is higher for a lot of teachers. Some might be a little bit lower, but I think 20 is a decent average. All right, so part A here, they want us to calculate the going rate, if you will, for a school teacher in units of dollars per hour per child. So this is what we want to find. So for a teacher, all right, and compare that of a babysitter. So basically, what's a teacher being paid in dollars per hour for every one of those children in their classroom? Okay? And how does that rate compare to babysitter, right? And then just to keep from diluting things too much, It says do not include the break time or any before or after school activities, lesson planning, etc. Honestly, there's a ton of extra time that goes into teaching, but we're just going to look at the very specific contracted hours here. All right, so this one's a little bit different, and then we got to write down a bunch of things to begin with. We need to pull a lot of information out of this problem, if you will. Okay. So if we look through here, first thing, the going rate for the babysitter in Chautauqua County, we said is roughly $5 per hour per child. So we need to know that. Okay. So what that's saying is for this problem, for the babysitter, $5 is equal to 1 hour of work, okay? And that's for each child. What else do we have in here? Average school teacher salary, so salary that would be how long they work for a year essentially, is $53,000. So we're going to say that $53,000 for a school teacher is equal to 1 year. All right, it's 1 year of teaching, right? It's one work year. It's not necessarily a year, but it's a work year. Okay. And they're contracted to work 180 days per year. Okay. So again, for that teacher, right, 180 work days is equal to 1 work year, if you will. So maybe I'll add that on these so we're not confused. 1 work year, 180 work days. And then we know that it says generally teachers work 7:45 a.m. to 3 p.m. with a 45-minute break. So we want to know how long they're working, but we don't want to include that 45-minute break. Okay. There's lots of different ways that you can do this. You can find out how long it is from 7:45 to 3 and then take those 45 minutes off. It's really up to you. Okay. I prefer to start at the 7:45 and just add those 45 minutes on to begin with. Actually, I would have broken it up completely differently, but let's just do that. So let's just say the break is the very first thing in the morning. So that's what we're not counting. So if we add 45 minutes onto 7:45 a.m., they're actually going to start at 8:30, right? 15 minutes would get you to 8, and then the remaining half hour of that 45 would be 8:30. So that means they're working from 8:30 to 3 if we don't count the break time. So if we do that, so 8:30 would be what? 9:30, 10:30, 11:30, 12:30, 1:30, 2:30, that's 6, and then still another half hour to get to 3. So they're working 6.5 hours essentially. 6.5 work hours is equal to 1 work day. Not word day, work day. I don't know why my pen's acting a little funny there. Oh well. All right, so let's do this. So we're just going to start with the teacher's salary. Okay, this is what we know they're getting paid, because what we want in the end is dollars, right, per hour per child. So let's just start with the dollars that we do already have for the teacher, which is the $53,000. But we know that that's per 1 work year. So we've used that one essentially, right? Just kind of like the other ones, we'll mark off the ones that we've used. Okay. We know if we work our way down the line here, we see the 1 work year here. So for a teacher, we know that 1 work year, I'm going to put it in the top so it'll cancel with the 1 in the bottom. 1 work year is equivalent to 180 work days. So we've used that one now too. Work years cancel out. And then we'll use our last conversion there. we see that 1 work day is equivalent to 6.5 work hours. I'm going to put the 1 work day in the top, so it'll cancel with the work day in the bottom I already have. 6.5 work hours in the bottom. And now we're essentially in dollars per hours worked, which is the same thing for a babysitter, right? It's dollars per the hour they work. Okay? So dollars per hour, let's go ahead and compute that out. When we do that, you should get roughly 45.3. I don't remember exactly what it was after that because I probably should have rounded to the cents, right? Okay, but $45.30 per hour. But don't forget, this is still for her entire class, right? Or his entire class. I shouldn't specify gender there, right? We want to know dollars per hour per child, okay? Because the going rate for babysitters that we're given is $5 per hour for each child. So we're going to take this rate that we have, the $45.3 per hour, and we need to make it per child. And we said as an estimate, we were going to have 20 as the average class size. So that'll be 20 children. When we do that division out, and I might have just kept this number in my calculator without rounding it. That might be why I just put the 3 here. Okay, so they didn't end up with round off error. You get 2.26, so $2.26 per hour for each child. Which is less than half of what a babysitter's making, right? So they're saying based on the average salary in our area, a teacher would only make $2.26 per hour for each one of the children that they teach, not counting any of their breaks, lesson prepping, after school activities, any of that stuff. So appreciate the local teachers that take care of your kids if you have, right? Even, especially during this crazy pandemic, right? We're all doing the best we can. All right, let's look at the second half. So this is still the same scenario. It's just a different question. The question this time says, if the average teacher were paid the same average rate per hour per child as the babysitter, calculate the average annual salary for a school teacher. Okay. So this time we want to find annual salary. Okay. And that's if they were paid the same as the babysitter. So this time, this is what we're saying is, take the babysitter rate and turn it into a salary. So if we remember, the babysitter rate was $5 per hour. So we're going to start with that, $5 per 1 hour. It is per child, just like the last one. We'll deal with the per child at the end. Anytime you have one of these mixed units within mixed units, if you will, it's easier to just kind of deal with one at a time, I think. And then we're going to use a lot of those same conversions that we did before, but backwards. Okay. So hours, or essentially work hours, right? For a teacher, if you recall on the last slide there, it was 6.5 work hours was equal to 1 work day. So we can cancel those hours. I put the 6.5 work hours in the top because right now our hours are in the bottom. Work day on the bottom now. And then again, same conversions that we already came up with last time. Work days, we know that for a teacher there are 180 of them in a year. So work days in the bottom, so I need to put the 180 work days in the top now, over 1 work year, if you will. That way I can cancel my work days. Right, and this would now be dollars per year, right? Work year, which is what an annual salary is. So we just need to compute this out, and this would give us just per one child still, right? Because this rate was for one child. When you compute that out, you should get $5,850 per year. And this is for one child, or for each child, if you will. And I've never hired a tutor, a private tutor for my kids. No way could I afford that. But I would imagine that this number is pretty low for that. So, all right. So now that's for each child. But again, we have that class of size 20. So we need to multiply that by all 20 children essentially. So I'm going to be a little lazy here and just say times 20 children, right? When you multiply those out, you will get $117,000 per year. Okay. So if a teacher with a class of 20 was getting paid that $5 per hour per child, working the bare minimum hours, they should have a salary of $117,000. Most teachers in this area that I know of do not make that much. All right, we're almost there. I think we just got one left here. Also by my colleague. You can tell I like these problems that he made because the last three I picked out were all from him. And you can tell it's not mine because I am not a good grandson. That just doesn't work. Okay. All right, but let's read through this real quick. It says, a while ago, I was visiting my grandmother when she complained that the faucet in her bathroom had been leaking for a long time. Being the good grandson and math professor that I am, I first measured the rate at which the faucet was dripping. 9 drops every 15 seconds. That feels important. Let's underline it. And then took the faucet apart to see that one of the rubber seals had deteriorated and needed to be replaced. A quick trip to Home Depot cost me about $4. That might be important, right, for the replacement seal. And within 30 minutes, maybe, right, we always underline these number parts, total job was done. No more leaks. As I reflected on this episode, I wondered how much money I actually saved my grandmother in her water bill by fixing the leak. When I received her next water bill, I saw that the Erie County Water Authority charges $2.96 per 1,000 gallons. That's gotta be important, right? Because it has the per in it. That's for the water usage. So the question in the end, notice going to the end is usually a good idea. So you can see your question, maybe even jump to the end right away before you read through it. Might be a good idea sometimes. It says, how much money did I save Grandma Teeny over the course of a year? So we want to know how much money did he save his grandma over the course of a year? So we're really saying how much money per year, right? So probably looking for dollars per year would be my guess. All right. I have a feeling that 30 minutes and the $4 are just extraneous information, because we really need to start with the rate the water is dripping in order to know how much water and how much money we end up stopping. The cost I don't know is necessarily needed yet, but we'll see. Okay. So let's start with that rate. That really is the important part here. 9 drops every 15 seconds. So we could say 9 drops per 15 seconds, right? That's kind of the same as every. So we're going to do that. So we have 9 drops per, so over 15 seconds. So 9 drops in the top, 15 seconds in the bottom. Somehow we need to turn drops into dollars and seconds into years. Okay. So let's start with Let's do the drops first. If we look at our US volume, I was surprised myself the first time I did this problem to see that drops is actually on there. I don't know what specifically a drop is. I don't know if they mean like one of those little droppers from chemistry, but it has an actual measurement here. If you look in the second row, we know that 1 fluid ounce is equal to 2 tablespoons, which is equal to 480 drops. Okay. So we know we have to use that. Drops is in the top, so I need to put drops in the bottom. And we know it's 480 drops. We just got to decide if we want the 2 tablespoons or if we want the fluid ounces. If I did the tablespoons, if I look on the chart, tablespoons would then lead me to teaspoons using the one above it. Okay. If I went to fluid ounces, if I go down, I can see that fluid ounces will lead to cups, and then pints, and then quarts, and then gallons, which is going to be more useful to us here because the cost of the water is given per gallon. So we're not going to use the tablespoons. Don't be afraid to try something, and if you reach a dead end, just go back and try a different way. Okay. We're going to use the 1 fluid ounce. So we have the 480 drops in the bottom. We're going to put 1 fluid ounce in the top. Drops cancel. And then we're just going to follow that volume along, right? So we know that 8 fluid ounces are in a cup. So we're going to put the 8 fluid ounces in the bottom so that my fluid ounces can cancel. 1 cup in the top. And then we know that 2 cups is equal to 1 pint. 2 cups goes in the bottom, so my cups can cancel. 1 pint in the top. We're getting there. We know that 2 pints is equal to a quart. 2 pints goes in the bottom again, so my pints can cancel. 1 quart in the top. We're almost where we need. We know that there are 4 quarts in a gallon. The 4 quarts goes on the bottom. 1 gallon on the top. So my quarts can cancel. We reach the gallons so that we can use the cost that we were given. Right? We need to put the gallons on the bottom. And it says it's $2.96 per gallon, or excuse me, per 1,000 gallons. That would be expensive if it was per gallon. So we have 1,000 gallons on the bottom equal to or equivalent to $2.96 on the top. So that my gallons cancel. So we got the money in the top, the dollars that we want. Now we just need to deal with our time. Our time is in seconds. So right now we're talking about how many dollars we save per second. It's got to be so incredibly minuscule that it's not worth computing at this point. So that's why we're going to look at per year. Okay. So I am still continuing this. I'm just going to move it down here since we don't have room there. Talking about time now. So if you need it, the time little bit of our sheet is there. Seconds, it's way back here in the beginning, but it is on the bottom. So I need to make sure I'm putting seconds on the top so it cancels. We know there are 60 seconds in 1 minute. So my seconds cancel. Minutes is not quite what I wanted. We know there are 60 minutes in 1 year, making sure we put the minutes in the top so that we can cancel them out. Or 60 minutes in 1 hour, excuse me. That would be a really short year. Let's fix that. One hour. There we go, much better. Okay. We know that there are 24 hours in a day. Again, we're just kind of following this right down, right? Put the 24 hours in the top so our hours cancel. Almost there. And then we know that there are 365 days in a year. We're not going to worry about that leap year. Put the 365 days in the top so that my days cancel, equivalent to 1 year in the bottom. So again, we can see we got our dollars in the top per year in the bottom, which is exactly what we wanted. Okay. Now we just need to go through Do all the multiplication, all the division. Be very careful entering this. Okay. If you have a graphing calculator where you can see everything, it might be better to actually put them, each one of these in parentheses as the multiplication, writing these as fractions. So like 9 divided by 15 in your first one, times that 1 divided by 480. That way you can scan through it, make sure that everything's written in there correctly. All right. If you do enter it correctly, it might take a while. And some of these numbers might get large, so it might be better to do, you know, the 9, divide by 15, divide by 480, you know, keep going. If it gets too tiny, you know, if you need to start multiplying and switching the order up, do that. Just so long as you get everything and you don't freak your calculator out. Most calculators are fine. I just know that some people have those really little calculators that are very basic, and sometimes they can't hold a lot of that. So avoiding really large numbers or really small numbers will help. So kind of bounce back and forth between the multiplying and dividing, so you don't get too large multiplying or too small dividing. All right, in the end, what this works out to be, and some of you are probably waiting, wanting to know if you got the right answer, is actually 91 cents per year. So all that work, that dripping faucet, and all he saved his grandmother was 91 cents a year. Now, I don't think in the end it was really about the money, because he spent $4 on the replacement seal, right, in half an hour's time. But now she doesn't have to listen to her faucet dripping, and he did something nice for his grandma. So, all right, that is it for unit analysis. This one was really crazy, so if you can do these long ones, excellent. As a reminder, there are a couple problems in the homework that refer to table or lesson 1.5. Some of the conversions are slightly different than the sheet that I gave you. That is on My Open Math. If you're having a hard time finding it, tell me. You just need to make sure you're using those conversions on those specific problems. Okay? If you don't, your decimals will end up off a little bit from what they want, and it'll mark you off, which is really frustrating when you know what you're doing. Okay? All right, that's all I have. Thanks for watching. This was a long one, so we appreciate it. I'll see you next time. Bye.